All right, Unit 8, Day 5, angles of elevation and angles of depression. I'm going to start by reviewing this thing called alternate interior angles, which is from Unit 2 in the fall. So what I have down here are a couple of parallel lines. And I know they're parallel because they have these arrows in them. And then what I also have are a couple of transversals. So transversals are just lines that cut across two or more parallel lines. So alternate interior angles are angles like this one and this one, these two red angles that I've drawn. They're alternate because they are on opposite sides of a transversal. Right, so this one is on the right side of this transversal. This one up here is on the left side of the transversal. Interior means between two parallel lines. Right, so both of these angles, these two red angles, are between these two parallel lines. So they're alternate interior angles. And the thing I know about alternate interior angles is that they are congruent, which means that whatever the measure of this angle is, let's say this one is 110 degrees, this one down here has to be 110 degrees, right? Or if I had this one right here and this one right here, if this one right here is 85 degrees, this one right here would have to be 85 degrees, okay? Those are alternate interior angles. And the reason we're talking about those first here will become clear once we start doing problems. Okay, the new stuff. What are angles of elevation and angles of depression? Well, just imagine yourself standing on a flat surface somewhere, and if you just looked straight ahead, that's kind of your line of sight, right? If you just look straight ahead at whatever's directly in front of you. Okay, if you compare that line of sight at whatever is directly in front of you to your line of sight if you were to look up at something. So let's say instead of looking straight ahead, now you're looking up at something up in the air. A tree, a bird, a ball, whatever. The difference between those two lines of sight make an angle, and that's called an angle of elevation. And so it could be looking at this one, maybe this is like 15 degrees, okay? An angle of depression is just the opposite, right? If you compare your line of sight, if you're looking straight ahead at something, to the angle that you would make if you were to look down at something. So let's say you're on a deck and you look down at someone's yard. Or let's say you're up in a tall building and you look down at the street or something like that. The difference between what your line of sight would be and your line of sight when you look down at something would just be an angle of depression. Okay, so again, angles of elevation are the difference between your line of sight if you're looking straight ahead and if you were looking up at something. Angles of depression are if you were to compare your line of sight straight ahead to if you were looking down at something. Okay, but up here I'm just going to focus on angles of elevation for a minute. So let's say this object up here is a bird. Let's say you're looking up at a bird for some reason. Your angle of elevation, or the angle from your perspective that we would call an angle of elevation of you looking up at the bird, is going to be equal to the angle of depression that the bird would have if it were to look down at you. Here's what I mean. So if this bird up here were to look straight ahead, its line of vision would be like that. But if it were to look back down at you, there'd be an angle of depression, right? What I'm saying here is that if you're both looking straight ahead, if you were both looking straight ahead, not looking at each other, your respective lines of vision would look like that, and they would be two parallel lines. If you were to start looking at each other, like this, you'd be creating a transversal, right? This blue line I'm sketching in here, or highlighting in, would be a transversal. What that means is that the angle of elevation of your line of sight up to the bird, let's say this is 20 degrees, is always going to be equal to the angle of depression of that bird looking down at you. So to fill in these blanks here, the angle of elevation from a person's line of sight to an object above it is equal to the angle of depression from that object to the person's eyes. Okay? And as you can imagine, it works the other way. So let's say you're in a building and you're looking down at a street. That's going to create an angle of depression. And let's say that angle of depression here is 22 degrees, right? From where your eyes are to where this thing down at the street is 22 degrees. Let's say there's someone down on the street who's looking back up at you. So their vision is going to be an angle of elevation, right? If they're looking from where they are down below up to you, their angle of elevation is going to be equal to your angle of depression. All right, so now let's start doing some problems with elevation, or angles of elevation and angles of depression. What we're actually going to be doing when you do problems with angles of elevation and depression is using the trig functions that we learned last week. And so this one here is a pretty easy example, but I'm going to walk through it so that it'll help you with problems 19b, 20a, and 20b on your classwork for today or for tomorrow. So we have this person shooting a hockey puck, and it's the first piece of information or data they give me is that they're 20 feet away from the goal, right? So that means that from right here, apparently where the person shot it, to right here, the goal line is 20 feet. And then it says it's a 5-foot goal. What it's saying there is that the goal is 5 feet tall. Okay, and then it says the puck travels at a 15-degree angle of elevation. So this right here, from where the puck started, right, if this person would have just shot it along the ice, it would have had a 0-degree angle of elevation. But when they hit it, it started traveling up in the air a little bit, so it has a 15-degree angle of elevation. They want to know if the player is going to score, and apparently the goalie's been taken out for some reason. So what it's really asking us is if a person is 20 feet away from something and shoots something at a 15-degree angle, by the time it travels those 20 feet, will it stay under 5 feet, or will he shoot it over the goal, basically? So as always, I'm going to redraw the triangle to kind of help me figure out what I'm doing here. So I know that this is 20 feet. I know that this is 15 degrees. I'm going to put a variable right there because I know the goal itself is 5 feet tall, but I don't know for sure whether the height of the puck after it's traveled 20 feet is going to be more or less than 5 feet. If I'm this hockey player, I'm hoping it's less than 5 feet. If I'm the other team or whatever, I'm going to hope that X is more than 5 feet because that means the puck's going to sail over the goal. Okay, so what I'm going to do here is I'm going to say, okay, well, I'm working with a 15-degree angle, and I'm going to set up a trig ratio. What sides am I working with? Well, one of the two sides I have is this X right here, which is an opposite. So I have an opposite. And then I have this 20 right here, which is the adjacent. So I have an opposite and an adjacent. If I were you, I'd go back to that table where I gave you all the information you need to figure out what trig ratio to use, but I just happen to know that opposite and adjacent means I'm going to be using tangent. So I'm going to say tangent of 15 degrees equals opposite over adjacent. All right. So then what next? Well, I'm going to figure out what the tangent of 15 degrees is. So it's 0.26, I'm going to say 0.268 equals x over 20. Now there's really just one more step. I'm just going to have to multiply both sides by 20 to get rid of that fraction. Those are going to cancel out, so x is going to be equal to whatever 20 times 0.268 is 5.36. So x is about 5.36. All right, so how do we answer this question? Well, what this is saying is that the height of the puck by the time it travels the 20 feet to the goal is going to be more than 5 feet. In other words, the puck is going to fly over the goal, so this person didn't score. Okay, number 7, example 2 here. Oops. Okay, so there's a pilot and he's flying through a storm and he's currently at an altitude of 528 feet. So he wants to land. So the pilot wants to land. It says he has a horizontal distance, that means like a left to right distance of 2,000 feet to land. So between where he currently is and the spot he wants to land, there are 2,000 feet. Again, he's 528 feet in the air, and they want to know at what angle of depression should he land. All right, so what I'm going to do here is I'm going to change the place where I'm putting these two, because if it wants to know the angle of depression, what we have to actually do is draw a straight line from where the pilot is to where he would be going if he just kept traveling straight ahead, right? What he's going to eventually do is he wants to veer off of that path that he would be traveling on. He wants to decrease his altitude so that eventually he's at 0 on the ground, right? So there's some angle of depression that he's going to use to land in 2,000 feet. He's going to travel from right here to right here. It's going to be 2,000 feet. Over that time, he's going to drop 528 feet. So I just kind of redid the triangle there. So what I have here are two values, two triangle side lengths, and an angle that I want to find. So I'm going to go back to the trig ratios. I'm going to say, okay, what do I have here? From the angle I'm looking at, I have an opposite. And the opposite here is 528. And what is this 2,000 here? Well, is it the hypotenuse? No, because if this is my right angle, the hypotenuse is over here. So this 2,000 is going to be an adjacent. Okay. So I'd go up to the table and I'd say, well, what do I do if I have an opposite and adjacent? I'd use the tangent. So the tangent of angle x equals opposite over adjacent. And before I can move on, I got to figure out what that is as a decimal. So 528, you always do the numerator divided by the denominator, and it's 0.264. All right, final step then, second function on your calculator, tangent 0.264, enter. And again, the keystrokes on my calculator are a little bit different than yours, but basically, oops, should get like 14.79 degrees. So basically, angle x would need to be about 14.8 degrees. You can round it up however you want. Okay, so what this is saying is that if that pilot wants to land in 2,000 feet, and right now he's at 528 feet, he's going to need to start diving at an angle of depression that's 14.8 degrees. Okay, last example, and then you'll be ready for the classwork problems. It says this person, Hugo, standing on top of the St. Louis's Gateway Arch looking down at the Mississippi River. The angle of depression to the closer bank is 45 degrees. So the picture they gave you here, or that I'm giving you, is kind of misleading. Basically, he's up here, and he's looking down at the river. And the angle of depression from his vantage point, allowing him to look down at the river right there, is, let's see if I can do a color that'll show up. 45 degrees. Right, so if I redraw that triangle down here so that the picture's not in the way, we have a situation like this. 45 degrees, and it tells me that the arch is 630 feet tall, so he's looking from 630 feet in the air. And the two sides of the triangle I don't know are the hypotenuse, which I don't need to know, and the adjacent side, which I'll eventually figure out. All right, that's one thing. Okay, then he looks across to the other side of the river. So he's looking over there. The angle of depression between his line of sight and the opposite side of the river is 18 degrees. Okay, so if I redraw that triangle, it would look more like this. The height is still 630 because he's at the same place looking, but now the angle of depression is smaller. Right? It's only 18 degrees. So I'm going to call that one Y. So what it wants to know is, based on that information, how wide is the river? Like, what is this distance right here? In other words, if I look at my two triangles, if this part of it is X and this whole thing here is Y, what's the difference between X and Y? In other words, what is Y minus X? That's going to be our answer, right? This whole distance minus just the smaller distance is going to tell us just how wide the river is itself. Okay, so let's figure out what X and Y are. For X, what am I going to do? Well, I have a 45-degree angle, and I have an opposite side, which is 630, over an adjacent side, which is X. What do I do when I have opposite and adjacent? Well, just like the other problem so far, I'm going to use the tangent. So the tangent of 45 degrees is going to give me 630 over X. What would it look like on this side? It's going to look very similar, actually, except I'm going to have a different angle that I'm working with, right? So I have an 18-degree angle, and that's going to be equal to the opposite, which is still 630, over the adjacent, which in this case is Y. And it's still going to be tangent because I'm still working with opposite and adjacent. Okay. Need to know the tangent of 45 degrees is just 1. Tangent of 45 degrees is just 1, which is going to be easy to work with. Now I need the tangent of 18 degrees. 0.324. All right. When you have X in the denominator, or as the denominator of a fraction, the only thing available to you is to multiply both sides of the equation by X, right? Because when you multiply a fraction, any fraction, by its denominator, it just leaves you with the numerator. So this one's going to be easy. X times 1 is just 1x or just X, and on the other side we have 630. So what that tells us is that this distance right here from where Hugo was looking to the nearest side of the river, this distance is just 630, not degrees, 630 feet. So what I want to know now is, what's the rest of the distance? What's this blue one right here? Well, before I can do that, I have to figure out what Y is. So just like I did on the other side, I'm going to have to multiply both sides by the denominator of the fraction. And so 0.324 times Y equals 630. Now I'm going to divide both sides by this coefficient of X. So 0.324. So Y is just equal to whatever 630 divided by 0.324 is. $1,944.44. Okay, so that distance is all the way from here, from where Hugo is, clear to the other side of the river. So if I want to know just this part, just in between here and here, I have to take Y and subtract X from it. right? That's going to leave me with just the length, or just the width, sorry, of the river. So the river equals y, which is 1944.44, minus 630. $1,314. I don't think I quite did that right. .44 feet. That's the width of the river.